Hi everyone, my name is Arash, and my study is about modeling suspended sediment concentration in northwestern US rivers. So, yeah, we all know wildfires are damaging and costly, and where I come from, northwest in Boise, we got a lot of them, and that's because the conditions are right. And we've got a lot of biofuel, all the drivers needed, and dry seasons that result in frequent wildfires. And when wildfires happen, we get a lot of sediment dumped into our river systems. And one of the products of wildfires is the ash, and the ash creates this hydrophobic layer in which water can't penetrate soil anymore. So we've got a lot of erosion happening and a lot of sediment moving into the rivers. Okay, so that was supposed to be a USGS video. It's not playing. Anyway, it shows how wildfires create huge runoffs and transport sediment easily. And that what they do basically replaces the saturation excess mechanism for runoff generation and kind of replace it with a Hortonian flow where we have infiltration excess mechanism. So it has many implications and it can be quite devastating, particularly for aquatic environments, for aquatic life, and it can hinder the dam operations and cost a lot for the stakeholders. According to the EPA, $16 billion average annually is spent for damages from the sediment and their suspension. So my studies uses two different approaches. One using satellite imagery, the other one is drones. Now, why drones and multispectral camera? Because most of the tributaries and small river systems are not wide enough for our satellite imagery, at least those that are free. So we've got Landsat and we've got Sentinel that are ranged from 10 to 30 meters, but to get to the small tributaries, we need a higher resolution ones. Now I see some USGS folks here. Though they have hands on some high resolution satellites, I'm talking about world views, and those go from 0.5 meter or less, so that's good. But our poorer students like me don't have access to that. So the alternative and the cheapest alternative is to use drones. Next slide. So we set up an experiment in laboratory where we collected three different soils. One is a sandy loam, the other one is sandy clay, and the other one is an ashy sandy loam, which was collected from a site that experienced a wildfire in the Boise area. And this is the tank that we built and the experiment we set up. At the bottom, we've got gravels. There's a pump inside the tank that circulates the water and then make sure that all the sediment stays suspended. And there's a multispectral camera mounted on top to take images at different concentrations. And we're changing also the temperature of the tank. So we have different observations. And this is our general model for modeling suspended sediment. We've got some temperature data that was recorded from the thermometer in the tank. That's numerical data. And we've got multispectral images from a MicaSense camera, which is a 5-band camera, RGB plus red edge and near infrared. And we do some data generation process before feeding it to different models, just to make sure we are not overfitting and we have enough samples. So for our models, we've got this custom built CNN model, a convolutional neural network, a unit model, and transfer learning using EfficientNet. And this is the unit model. So I've made some changes to the original unit model. So I've shrunk the input image to make it computationally more effective or less demanding. And then at the output, instead of segmented in map, I'm producing one output, and that's the suspended sediment concentration value. And this is the EfficientNet, which was proposed by Penn and Lee in 2019 from Google, which was very, very clever. What they did was to, I mean, I'm sure all of us have experience when it comes to convolutional networks and building them, that we start from a very simple model and we add more complexity to it. But how does that happen? That's a random process. So you kind of double the scale. We call it wide bit scaling. We kind of double the bits. We increase the feature maps sizes, or we can double the depths, like shown here. We can increase the number of layers that we are using, and these are all random processes. I'm saying double. You can triple it, but or increase the resolution of our input image. So we make our feature maps bigger, and then we kind of upscale and feed it to the model. But what they did when they proposed was compound scaling. So do all of these 3 steps in one go. And that's really clever idea. And the figure on top right shows the performance of EfficientNet when you compare it to its predecessors, such as Inception, Resonant, and others. You can see that it achieves higher accuracy with less number of parameters. So yeah, this is the structure that I came up with for transfer learning using EfficientNet. We got our numerical data and we got our image data. There were 4 different configurations. One configuration was considering the temperature data. One was not considering the temperature data. The other one was considering the fine tuning. So in the fine tuning, we kind of retained the last 20 layers of EfficientNet. We trained them based on our own imagery. And then, but we leave the batch normalization layers alone because those take a lot of time to train. It doesn't really yield improved performance. And the last one is without fine tuning the EfficientNet. And this was interesting. This is the result of, and this is the result of some of the feature maps in the EfficientNet. It was kind of interesting to me. On the far left side, we've got our inputs. And as we go down, we are increasing the suspended sediment concentration. And if you look at layer 257 and look past that, we can see that it's no longer visually sounds like our original data. So it's interesting to kind of see this process. And after that, it's just, I think, machine language. And these are the results for different models. We've got random forest, XGBoost, custom CNN, the UNet, and EfficientNet. But UNet and EfficientNet had the highest performance. The rows on top show the predicted in red and the actual in black. And in the middle, we can see the residuals for each of these models. It's interesting that although UNet and EfficientNet had the highest accuracy, as we move toward high concentrations of suspended sediment, we can see that the error is kind of increasing. We can see it in the slide here. It's going kind of down. So we have reduced performance there. And the final plot shows final row shows the QQ plots for different models. And yeah, so this is general figure showing different models and basically showing the 2 top models that we picked. So the best one was the fine-tuned EfficientNet V3 with 184 layers, plus the temperature data, and the other one was the UNet. The next step for this study was to look at now the satellite imageries and see how we do on satellite imageries. So we've got AquaSat. This was a data set that was published, I think, in Scientific Data. And they have point estimates of suspended sediment concentration in each location of the suspended sediment gauges, and they have all the Landsat bands mean and standard deviation values recorded for the entire US. So we basically took that data and we trained it only on the Western US, that black bounding box you see. And this is the figure to the right just shows the distribution of different bands with respect to suspended sediment and themselves. And this is the result. So we tested different models. We got auto boosting, SGD, XGBoost, random forest, and deep neural network. The best one was deep neural network with the R square of 0.7. So it didn't do relatively good, and it's mainly because we're taking point estimates and not the images. So what's next for our study is to now look at, to kind of delineate river systems and look at the imagery and do a convolutional neural network instead of a deep neural network, or 1D instead of 2D instead of 1D. And the one to the far right shows the correlation between different bands. And if you look at the final row, that's the TSS, and we can see that near infrared, the green and red bands are the most important and the most highly correlated with the TSS. So those can be useful in predicting the total suspended sediment concentration. And that's, thank you.
Any questions? Okay. Could you go to your last slide? Yes. So here, why you are using like this is simple regression, because I have to like up to 500, with TSS value all the.
Okay, yeah, you're talking about the line.
Yeah, actually, the simple regression.
Yeah. So that's yeah, I put that there as like to show like a QQ plot. So that's like the middle row. So if our data revolves around, that's not actually that's like a simple fit. So if our data revolves around this fit, it means we're doing really good. But in this case, we can see it's a scatter. So it's just the way to show, like in QQ plots, how close are we from observed to the predicted.
Yeah, I understand that one. What I'm trying to say is like most of majority of your points are like considering the smaller point, like up to 500. So like, do you have any other suggestion? This kind of to show this kind of data.
Yeah, one of the problems we saw even in the laboratory experiment was that the models weren't doing really good when it comes to high concentrations of suspended sediment, because the water gets really muddy, and I mean, it's not us, but even looking at it from our view, the difference between muddy and muddier water is not really clear. I think that's where the models are struggling when it comes to very high concentrations, and we can see.
Do you think like transformation may be benefit?
We did do transformation of original data. So data were standardized and rescaled. Yeah.
So you tank, right? When you take image, does water move, or you have to stir that all the time?
The water moves. There's a little turbulence because there is a pump in the water, but the way if we go back to the I don't know, maybe eight. Yes, six. So if you look at this image, we see the problem comes with the moving water when we have reflection from the top. So we made sure that there is no reflection by like when this experiment is happening, all the lights in the room are off. Only these two projectors are on. And these two projectors are, if they are less than 45 degrees, they will not produce any glare. So even if the water is turbulent a little, it's not going to show in our image.
You want to make sure the concentration is kind of uniform distributed, right?
Yes.
So you take the pictures. So in order to keep it uniform distributed, you have to keep stirring. Right?
Yes.
Otherwise, it's settle.
Yes, indeed. Yeah. So yeah.
Have you thought about the distribution, vertical distribution, concentration, in terms of the image quality, how it's going to affect itself? Because in gravity, it's not never going to be vertically distributed because of gravity.
That's true. That's a really good question. That's something that actually can be done. We unfortunately didn't do it, so it would have been nice to take samples from different depths, and that would. I mean, in this small tank, it wouldn't have really mattered because we're circling water so fast, and the depth is not that much. But in actual rivers, that's something to be really considered. If we collect samples at different depths, we're going to get we can train different models on different depths, and that would be a better estimate. That's true. Thank you.
Yeah, can I have one last one before moving to the second one? And we can have more time in the later discussion session.
So you're looking at like one of kind of three key like optically active water quality constituents. You're looking at suspended sediment.
Yes.
But when you try to move from your lab experiment to like a real river, you also have like color dissolved organic matter and chlorophyll and things that in combination with suspended sediment might lead to the same color that you see, but not necessarily the same like sediment load. Have you thought about trying to control for things like chlorophyll and CDOM in your models?
That's an excellent question. No. So the laboratory experiment was just a suspended sediment, but the AquaSat dataset, they only, I believe, I'm just thinking top of my head, but I believe they only recorded suspended sediment also. But there are stations that record the algae and different concentrations of different other chemicals in the water. But that's a really good point. If you have the same model, if you go back to go forward to right there. So we can use this same model on satellite imagery, the same principles. And instead of having one output as our suspended sediment, we can have 4 or 5 outputs at the end, like the concentration of algae and the other stuff, as long as we have measurements on ground that are recording those. But yeah, that's a great point. I'll definitely take that into consideration.
Yeah, that'd be cool. I'd love like a multitask model that thinks in all three.
Yeah. Thank you.